Welcome to Lecture 2 for PIC Microcontroller, Delay Subroutines and Timers. In this lecture, we'll look at a few examples of microcontroller controls in our everyday lives, and that's specifically the refrigerator and the washing machine. We'll go through an example of flashing LEDs and look at the delay subroutines available. And finally, we'll look at a feature of the PIC18, which is the timers modules available on our PIC18 F67J50. So in a typical controller system, we have our human interaction over here, which contributes to the embedded computer. And so this is where the computation occurs, and the computer actually does its computations and controls the compressor and the alarm and the display. And that's based off the actual and required temperatures inputted by both the human and the system itself. So before you write down any code, as we're in a design phase, it's a very important phase because this is where you sort out the important key aspects and specifications of your design. And what many people do straight away is they start writing these spaghetti code. So spaghetti code is just a bunch of these unstructured code that usually people start writing as soon as they start thinking of a problem, rather than taking a step back and figuring out what the problem is and designing the program to be such a way that it's useful for the human as well as for your computers themselves. So step one, most importantly, is actually representing your problem in a diagram. So here's an example of one of these diagrams. So this is what's known as a block diagram. So each major component is represented by a block. So as you can see in the middle, we have our microcontroller. Now we have two inputs, which are denoted by the direction of the arrows feeding into or outside, coming out from the microcontroller. So in our case, we have two inputs and two outputs. And the output is controlling the compressor and also controlling the alarm. From the block diagrams, you then want to look at the flow of the program. And in this example, we have what we call a flowchart. So it's a chart that basically shows what occurs based on the direction of the arrows. So in our example of the refrigerator, we read the actual temperature, and then we read the required temperature and do a comparison between them. And based on the comparison result, we will either activate or switch off the compressor. Now, this is kind of a bang-bang controller, so it's an on or off controller, but this is a simple way of doing it. And if we run into problems, we then do a simple check, so see whether the actual temperature is way above our desired temperature, then we activate the alarm or not. Now let's look at a more complicated example. So here is another way of representing your program code, and this is what we're called as a state diagram. So depending on where we are in a specific state, and then based on the actions, the state diagram would then go from one state to the next. So in our example, we switch on the washing machine, and then when the door is closed, you start the cycle. So filling with water, you heat the water, you wash, you rinse, you spin, and then you go back to the ready state. So this is just another example of representing your program in diagrams before you start writing spaghetti code. And in this example, this is a typical cycle, it's a typical state diagram for a normal washing machine. Let's look at our problem of the flashing LED. So we have three LEDs, which are green, yellow, and red, and that are attached to port B of bits 0 to 2 in our PIC18. So let's say we want to write a program that toggles the three LEDs every half a second in this specific sequence. So green, yellow, red, and so on. And for this example, we assume that the system clock is 20 megahertz. So if looking back into the previous slide of state diagrams, we can represent this problem as a state diagram. Now, from the state diagram that we obtain, we can then design our code in such a way that it mimics the state diagram. And that in turn allows us to have a clearer picture of what needs to happen and where an issue might occur. So let's look at the flowchart for this top level, what we call the top level of our program. Now we have three main parts that we need to look at that our microcontroller needs to achieve. So firstly, we have the initialize. So we need to initialize port B. We need to initialize the relevant counters and variables required for a 500 millisecond delay. We need to look at how the microcontroller will blink. So that's how it toggles the LED in this specific sequence. So it's green, yellow, red, green, yellow, red. And then we know that the LED to be toggled is determined by the previous state. And finally, we need the microcontroller to be able to perform a 500 millisecond wait. And this whole program, top level flowchart, can be represented as such. So we have our initialization, we have the blinking of the LED, and then we have the 500 millisecond wait, and then that cycle repeats itself. So let's start looking at the initialization. So firstly, we know in our example we're using port B to put our LED outputs, and specifically the lower 3 bits of our port B as outputs. So first we need to clear the port B bits, so we can initialize them as specifically the last 3 bits as 000, and then there's one other step that we need to do, and I'll leave that as an exercise for you to do. So first we need to set up port B, so we need to clear the port itself, and now we also need to set them as an output. So specifically we need to set the last 3 bits of port B to be an output, and I'll let you do that, and I'll give you a hint to use the data sheet, specifically what registers you should be using to change the direction of the pin input outputs. Now let's look at blinking the LED. So we want the LEDs to be toggled in this specific sequence, a green, yellow, red, and then based on the lower 3 bits and the LEDs that we have available, we have 3 specific LEDs, and they're situated at bits 0, 1, and 2. So as you can see, 001 coincides with green, 010 coincides with yellow, and 100 coincides with red. And in that way, we can determine the next LED to be toggled by what the current state is. So now we have a numerical or binary way of representing the states themselves. So the flowchart, again, we're using a flowchart. So the flowchart would look like this. So let's say we're reading the current state and check whether it's green. If it is, then we need to toggle it to yellow. And then if it's not green, then we check whether it's yellow. And if it's not yellow and it's not green, then it must be red. So from red, you need to toggle it to green. And then from there, that subroutine would then return. And obviously after the 500 millisecond delay, you would repeat this process. So let's look at our C code. So let's say we have a function called blink, so void blink. So that's the function called blinking, and we're checking is the bit high. So we're trying to check if it's green. So the 3 bits between bits 0 to 2 is 001. Now, since only one of the bits can be activated at a time to indicate which state it is in, we don't need to check all 3 bits. We just need to check the relevant bit. So in our case, we just have to check whether the green bit is on. And if it is, then we need to toggle it from green to yellow. So let's call toggle1 a function to toggle from green to yellow. And if it's not green, then we check the second bit, and this is to check if it's yellow. So similar, we're checking bits 1 instead of bit 0. And if it is, we then have another function called toggle2, which toggles from yellow to red. And since if it's not green and it's not yellow, then it must be red. So we want to change it to green. So have a look at what we do here. We're setting the output of bit 2 to be 0. So that's the 1 in your state. And then we're setting bit 0 to be 1. So in this case, we're switching off the red LED and we're switching on the green LED. And then at the end of it, we would have a 500 millisecond delay. So let's just represent that 500 millisecond delay as a function called delay 500 millisecond. Now, let's continue through this with our 2 functions that we've done. So we have toggle1, which is changing from green to yellow. and toggle 2, which is yellow to red. Now I'm just going to let you take a couple of seconds, just quickly see if you can finish this. So if you refer to the previous slide, you should have some idea of what needs to happen and what bits to change specifically. And come back in a few seconds and we'll discuss the answers then. Now, assuming that you have paused the video and you have attempted this yourself, so let's look at the answers. So toggle 1 is to change from green to yellow. So notice how bits 0 is 1, indicating that the green LED is on. Now we want to switch it off and then switch on the yellow LED. So in our case, this would be port B bits.rb0 is equals to 0. So remember, equals means assigning a specific value, whilst if you have a double equals, that's a comparator. So that's saying if port B bits rb0 is 0. But in our case, that's not the point. In our case, we are assigning bit 0 to be 0, and we're assigning bit 1 to be 1. And then similarly, we have toggle 2, which is turning from yellow to red, and we do the same thing. So we're clearing bit 1, which is the yellow LED, so we're switching it off, and we are setting bit 2, which is the red LED. And now we have this other function called delay 500 milliseconds. And how do we implement this 500 millisecond delay? Now, in our normal lives, we just look at it as, yep, we'll just wait for 500 milliseconds, but a naive way to do this delay is to just tell the microcontroller to do nothing. And an easy implementation of this is in this section of code. So you tell it to wait a millisecond. So while counter is less than 500, each one of those indicates a millisecond has passed. The microcontroller just waits for a millisecond. And once the 500 milliseconds has passed, then you continue on to the next section of your code. Now, while you tell the microcontroller to do nothing or wait for a millisecond, it is constantly busy checking. So what we call is busy checking. So it just stays busy, just waiting for the 500 milliseconds. And this is very inefficient. So remember that your PIC runs at 5 megahertz. So 20 megahertz crystal will mean that it's a 5 megahertz internal clock frequency. So while you're telling it to wait for half a second, the PIC has run 2.5 million cycles. So that's very inefficient. So let's look at this internal frequency. So you always have a crystal frequency and an internal frequency. So let's say we have a crystal frequency of 4 megahertz. Your internal frequency is always a quarter of this oscillating frequency. So in our example, our internal frequency would be 1 megahertz. So if you remember from first year physics, frequency is the amount of occurrences per second. So a million hertz means there's a million cycles per second. So for 1 millisecond, that's the equivalent of 1/1000th. So then in order to wait for 1 millisecond with a 4 megahertz crystal frequency chip, you would have to wait for 1,000 cycles. Right, so as you can see over there, just clear this up. So given a 4 megahertz crystal, our internal rate would be 1 megahertz, and therefore you're waiting for 1,000 ticks or 1,000 cycles. So if you remember from lecture 1, we talked about in the PIC system, in assembly, pipelining allows us to count how many ticks each instruction takes. So every instruction takes 1 tick, and every time we branch, it's 2 ticks. Now, in the low-level language such as assembly, it's easy to be able to see all the to calculate how many ticks each instruction will take. But In a high-level language such as C, there are libraries which handles the conversion between the C syntax and assembly, so you start losing sight of how many tick counts your instructions are actually taking. Now, so this means that we don't have our software code to be able to count how many ticks. So telling your code to wait for specifically 1 millisecond is almost impossible unless you're using assembly. So since software is unavailable, there are hardware modules which allow you to do that. So if you think back into lecture 1, we have these peripheral modules, and one of them is called a timer.